In this video, we're going to talk about quadratic surfaces. We're going to be able to identify a cylinder as a type of three-dimensional surface. We're going to recognize the main features of ellipsoids, paraboloids, hyperboloids, but not graboids, because that's a different movie. We're going to use traces to draw the intersections of quadratic surfaces. I'm going to explain what a trace is. We're also going to explain what a ruling is. If we look at a cylinder the way that we are familiar with, like a can of soup or something, in two-dimensional space, the equation x squared plus y squared is equal to 9 is a circle. The fact that z is not part of the equation means that z can take on any value, an infinite number of values, and it ends up forming, if you restrict the z, it'll form that can of soup, as you would expect. We're going to now define what it means to be a cylinder. The set of parallel planes, a set of lines parallel to a given plane passing through a given curve is known as a cylinder. The parallel lines are called rulings. So if we take a look at this shape, the rulings here are these lines that are running parallel to the z-axis. These are my rulings. Not these going around in the circle. These lines that are running parallel to the z-axis are my rulings. From this definition, we can see that a cylinder in three-dimensional space can take on different shapes that are not necessarily circular, provided, of course, that it has rulings that are parallel to that have parallel lines, that it can be made up with a group of parallel lines. So if we take a look at this example you can see is not circular. The shape is not circular. However, it can be made up with a bunch of parallel lines. In this case, my parallel lines are running parallel to the y-axis. These red lines are my parallel lines. These are my rulings. When we are sketching these three-dimensional spaces, it's useful to figure out what it would look like on a singular plane instead of in three space. And we call that our traces. So if we take a look at our sine wave here, I have the z. So here's z is equal to sine x. The trace on this z is equal to sine x on the xz plane, so those are the two variables that are being used, is the regular sine wave. Because y is not given, y can take on any value, and you can see here's my y-axis, and these lines are running parallel to that y-axis. Now, I do want to mention that you can have cylindrical shapes in which all three variables are being used. It's just a little harder to graph, and it's a little harder to see what the rulings are because it won't necessarily be running parallel to an axis. It's going to be running parallel to some line in three space. So I do want to mention that we have that. We're not going to spend much time on that in this class because you'd really want to have a 3D graphing tool to see a really good view of what it would look like. If I'm asked to sketch and describe the cylindrical surface of the given equation, I look to see if there's any variables that are not given. In example A, I know that the y is not given, so y is the variable that can take on any real number. So if I go to graph, here is my y, here's my z, here is my x, and here is my y. Now, if I look at what this would look like on just the zx plane, the zx plane would be a circle centered at the origin with a radius of 1. So it would then, if I then try to graph this in three space, I know that the xz plane which is the one facing this way, would go something like this. It would be centered at the origin with a radius of 1. Now, my y is the value that can take on any real number. And so I would end up with, if I wanted to cut it, say at that end of y and then at that end of y, that would be my cylindrical surface. My rulings would be running parallel to the y-axis in this direction, and that's what it would look like. My example here on B, it also has the variable, the free variable, which is y. So I would graph what it would look like. I'd find the trace of what this would look like on the xz plane. So here's z, and here's x. On the xz plane, this is the cosine wave that has been moved to the left, pi over 2. So in other words, what I have is the sine wave. So I have the sine wave. And then at 2 pi, here is 1, positive 1. That's a terrible one. That is positive 1. This is negative 1. Here's pi. Now, on 3 dimensions, I know what the trace looks like. This is my trace. I also know my rulings are parallel to the y-axis. I had this professor when I was in college back in the Stone Age that could make beautiful 3D drawings with chalk and a piece of string. You unfortunately do not have that kind of professor. This kind of professor cannot do these beautiful drawings with a chalk and a piece of string. I can barely even make a stick figure. So what this would look like, as best as I can, here is my axes. Here's x, here's positive y, here's positive z. So the trace would look something like this in the 3 space. So bear with me that this is not like the best drawing you've ever seen in your entire life. So it would look, going with a positive x-axis, it would come up and then it would come down like that. And then it would look something like that. And then my traces would be in this direction. So I'd have these maximums here. And then my minimums would be down here. So there's like a minimum. And I'd have all of these going in this direction. Terribly, terribly bad drawing, but that's what it would look like. 3 space. It's not a stick person, so it's not bad for me, just saying. Looking at C. C also has the variable, I made my life bad. I made my life bad because this is so much harder, by the way, than if I would have just said, okay, let's let this one be y, because this is going to make my life a little bit easier. The trace in the zy plane is going to be something that looks like this. It's the exponential function. That's what the trace is going to look like. Now, my rulings are going to run parallel to my x-axis. So here is z, here is y, and of course coming out is my x-axis. So here is my my exponential function, and then I'm going to have these rulings. They're going to look like that. So just kind of close your eyes, kind of squint a little, maybe shut the lights off. It's all good. So it is in your best interest to consider trying to get an idea of what they look like. So when you put them into a 3D type of software, that you'll have an idea of what it should look like. So knowing what the trace looks like and knowing which way the rulings are going, that's going to help you. Stresses me out to try to draw stick figures. Let's talk about quadratic surfaces. So quadratic surfaces are going to go back to the way that we looked at quadratic surfaces in 2 space. But now we have 3 space. So I want to make note that the a will belong to the x squared, the b will belong to the y squared, and the c will belong to the z squared. That's different than it is in 2 space. Now remember, in 2 space, it would have been ax squared plus bxy plus cy squared, and then etc. Because we're in 3 space, the way it works is the a will go x, b will go about y, c will go with z. D will be the xy coefficient, E will be the xz coefficient, and F will be the yz coefficient, and then we get all the way down to the constant. There are so many surfaces that are available to us for 3 space. So we're just going to hit some of the big ones. The first one is an ellipsoid. Now, within an ellipsoid, a squared, b squared, and c squared. If a, b, and c are the same thing, then we have a sphere. And of course, the a, b, and c, if they're not, is how far we, if we take the square root of them, is how far we go out in each direction. So if this would have been 16, then in the x direction, I'd go 4 from the center. These, of course, can go off of the center being at 0, 0. The b, take the square root of that, and that's how far I go in each direction for the y, and the z is how far, the c is how far I go in each direction for the c when I take the square root of c. Okay? In the traces, so when you look at the z-plane, that we have an ellipse on each one of our traces, of course, unless they're all equal. A hyperboloid, it depends on who's negative. Now, we notice that the x and y are positive, so we wrap the hyperboloid around the negative, which is the z. The next we have is a hyperboloid, which ends up becoming 2 sheets, so it's not connected. So this is like a cooling tower on a power plant, and this one is like alien software. So 2 cups that are never touching, that are just kind of floating in space, sharing the same axes here. Notice the notation here is that z is positive and x and y are negative coefficients. So it'd be z squared, negative x squared, negative y squared over c still goes with z, a still goes with b, or a still goes with x, and b still goes with y. We have the elliptic cone. With the elliptic cone, we have the a goes with x, b still goes with y, c still goes with z, and we have a negative here. We have the elliptic paraboloid, not a graboid, but a paraboloid. Notice that z is not squared, so the paraboloid is going to be cupping the z-axis. I could have had the x not squared, and I would have been cupping the x-axis. I could have the y not squared, and I would have been cupping the y-axis. And then, of course, we've got the saddle, the hyperbolic paraboloid. Z is the linear one. So we are going to have this saddle that's going to be along the z-axis. If x would have been the one that would have been linear, then I would have had the saddle along the x-axis. And of course the y, if it would have been along the y-axis like that. So for elliptical paraboloids, to find the location of the focus, you want to consider the trace in each plane and the standard form in 2D. The standard form in 2D would have been if it was x squared, it would have been x squared is equal to 4pz, where p is the distance from the vertex to the focus, or from the vertex to the directrix. So we want to think about the traces if we needed to find the location of the focus. So for this, they're asking us to find the trace in each plane, and then we want to write the equation in standard form and then identify the quadratic surface. So to find the trace, here's the trace. The trace in the xy plane, we set z is equal to 0. So if we set z is equal to 0, then the trace in the xy plane would be negative 4x squared plus 25y squared is equal to 100. So I would divide both sides, or everything, by 100, and so I'd have x squared, a negative x squared, over 25 plus the y squared over 4 is equal to 1. And we know the trace then in the xy plane is a hyperbola. That in the xy plane would be hugging the y-axis. So in the xy plane, it would look something like this. Okay, now I'm going to do the trace in the YZ plane. In the YZ plane, we're going to let x equal 0. And so I have 25y squared plus z squared is equal to 100. And so I'd have y squared over 4 plus z squared over 100 is equal to 1. So in the YZ plane, we end up with an ellipse. Now the trace in the, what's the one that's left? So I did x, y, y. So the trace in the xz plane, we let y equal 0. And when we let y equal 0, we've got negative 4x squared plus z squared is equal to 100. So we have x squared, negative x squared, over 25 plus the z squared over 10 is equal to 1. So the trace in the xz plane is again a hyperbola. We're going to be hugging the z-axis. So this is my z-axis, this is my x-axis. So let's go back and write this in standard form. We found all the traces. Let's write this in standard form and see if we can identify the type of conic. So the first thing I'm going to do is just divide everything by 100. So when I divide everything by 100, I'm going to get x squared. And this will reduce to the 25. Don't forget the negative. And then plus the 25 will reduce to y squared over 4. And then plus the z squared over 100 is equal to 1. A is equal to 25. A is equal to 5. A is equal to 5. B is equal to 2, and C is equal to 10. Let's just reorganize this with the y squared first. So y squared over 4 plus z squared over 100 minus the x squared over 25 is equal to 1. Because of the fact that this is negative, I have one that's negative, we know that this is the equation for hyperboloid. And not only do we know it's a hyperboloid, we know that for the hyperboloid, it is going to have the axis of symmetry will be the x-axis. Now, I kind of knew that this is going to be hyperboloid because of the shape. And I also know this is going to be a hyperboloid of one sheet. The reason I knew it was from one sheet is because of this. Do you see how that xz plane is, so here's Z, and here's Y, and here's X. The XZ plane, or the YZ plane, had an ellipse there. Because it had an ellipse there, I knew that that's why I had one sheet. And so the hyperboloid would look something kind of like this, and then something like this. So it'd be like this here on the side, like that. Now, how far everything goes out is like we do in 2 space. We know on the XZ plane that if this, or the YZ plane, if this is Z and this is Y, I would have gone from the skinny part, like the waist, if you will. The Z part would have gone out 10 in each direction because it's the square root of that. My Y would have gone out 2 in each direction. So things that we learned in 2 space, when I'm looking at my trace, will still hold true. Okay, let's take a look at this example. Now this is an example that's a little bit more interesting in the fact that this one needs to have the square completed. So that tells me that I'm no longer centered at the origin. So my previous example, I didn't have anything I really had to worry about. I didn't have any linear X's or linear Y's or linear Z's. Now, of course, I can, because of the XZ term that I could have, or the YZ term, that means I could have a rotation of axes in 3 space. We're not doing that right now. What we're going to do is go ahead and just put this in the regular standard form. So anything that has an X will be lumped together. So X squared minus 6X. Anything that has a Y will be lumped together. So plus 4Y squared minus 16Y. Anything that has a Z will get lumped together. So minus 4Z and then minus 16Z. And anything that is not attached to a variable will get moved to the other side. I'm going to start by completing the square on my X's. So it'd be X minus, I take half of 6, divide it by 2 and square it. So X minus 3, the quantity squared, which means I need to add 9 here. This one I do need to factor out a 4 first. When I factor out a 4, I'm going to get Y squared minus 4. So I take half of that, divide it by 2 and square it. So this will be Y minus 2, the quantity squared. So I need to add not just 2, not just 4, but I need to add this. To complete the square, I had to do have added 4, but I've also added this 4 as well. So it is not just 4 that's going to be added, it's going to be 16. And then I'm going to do my Z. My Z, I need to pull out a negative 4 first, and then I'm going to have Z, and that should be Z squared. And it's going to be similar. I'm going to pull out a negative 2 and square it. Now, as before, what I really have here is 4 multiplied by this 4. This is going to be a negative 4 multiplied by that negative, or that 4. So I end up subtracting off 16. So where I am now is I have X minus 3, the quantity squared, plus 4, Y minus 2, the quantity squared, minus 4, Z minus 2, the quantity squared, is equal to, and I have 4. Now, it's not in standard form yet, so I need to divide everything by 4. So I have X minus 3, the quantity squared, divided by 4, plus Y minus 2, the quantity squared, divided by 1, minus Z minus 2, the quantity squared, divided by 1, is equal to 1. My center is at 3, 2, and 2. Where's my center is? It has one negative variable that is squared. And it's a hyperboloid of one sheet. And its axis is going to be, its axis of symmetry will be the z-axis, because that's the one that's negative. And I did subtract, I pulled out a negative, so that does change the sign. Should make note of that. There we go. how to fix that. And so its axis of symmetry, it's going to be hyperboloid. Will be the z-axis. So the one that is negative is where the axis of symmetry is. Okay, so for this last example, what we're asked to do is find the equation of the ellipsoid that's centered at 1, 1, and 0 and passes through these points. So what we do is just like we did in 2-space. We start out with the equation, which is x minus 1, the quantity squared, over a squared. And then plus, because it's an ellipsoid, all will be positive. Y minus 1, the quantity squared, over b squared. And then plus z, and it happens to be 0, the quantity squared, over c squared is equal to 1. Now, given the fact that this has to go through 6, 1, and 0, 4, 2, and 0, and 1, 2, and 1, let's start out with the first point. Starting out with point A. If we start out with point A, we have 6 minus 1 squared, because remember my point A is 6, 1, and 0, so we're going to replace my x's with 6, my y with 1, and my z, of course, with 0. So I get 6 squared, or 6 minus 1 squared over a squared, plus, and then I'm going to have 1 minus 1 squared over b squared, and then plus 0 minus 0 squared over c squared is equal to 1. So what I end up with is this obviously goes to 0, and this one goes to 0. So I'm going to end up with 6 minus 1, which is 5 squared, so 25 over a squared is equal to 1. So I know that a squared is equal to 1. Or a squared is equal to 25, which is funnier than 24. Anyways, moving on. We're going to go through the next point. We've now found the a squared. Let's look at our next point. So now we're going to look at point B. Point B is 4, 2, and 0. So wherever I see x, I'm going to replace it with 4. So it's going to be 4 minus 2, the quantity squared, over 25, because we know what a squared is, plus, and then I have 2 minus 1, the quantity squared, over b squared, and then we know it's going to be plus 0 is equal to 1. The only variable that we now have is the b squared. So I have 4 minus 2, which is 2, or 4 minus 1, I don't know where the 2 came from, 4 minus 1, oh, it's because, 4 minus 1, which is 3, the quantity squared is 9, so I have 9 over 25 is equal to plus, before we get to the whole equal negation. And then I have 2 minus 1, which is 1, so 1 over b squared is equal to 1. By subtracting 9/25 from both sides, I get 1 over b squared. 1 minus 9 over 25 is going to give me 16 over 25. That tells me that b squared is going to be the reciprocal of that, so 25 over 16. Now we're going to use the point C to find my z value. So I'm using the point C. My point C is 1, 2, and 1. So I have 1 minus 1 squared over 25 plus 2 minus 1 squared over 25 sixteenths, so 25 sixteenths, plus 1 squared over c squared is equal to 1. This goes to 0, so that's kind of nice. And then 1 minus 1 squared is just 1 squared, so it is the reciprocal, so it's 16 over 25 plus 1 over c squared is equal to 1. I subtract 16/25 from both sides, and I get 1 over c squared is going to be 9 over 25. So c squared must equal 25 over 9. Now my equation then, I'm finally ready to give me my full equation in standard form, is x minus 1, the quantity squared, over 25, plus y minus 1, the quantity squared, over 25 sixteenths. And then plus z squared over 25/9 is equal to 1. And that's it for this section.